Hi there, Lewis Dan and Parry from Edera here, and today I'm going to give a demonstration of MCPee, when MCPs leak information. So this demo is going to consist of what is an MCPee, why you should care about MCPee, and the MCPee demo itself, the problem that we can see from that, and our solution at Edera, and we'll close with a conclusion. But let's start with what is an MCPee. Now, when we use an AI agent, so whether that be Claude Desktop or ChatGPT or wherever that may be focused on AI, there is so much information available to it. What is the right information to use? And that's the problem that Anthropic saw earlier in the year. The most sophisticated models are constrained by their isolation from data, trapped behind information silos and legacy systems. Now, that's probably you today within your enterprise, or even, say, your personal information. You don't want that personal information or that enterprise information on the public internet. So how is the AI agent going to be able to capture that information? Now, we've seen that people might, to date, share their secrets, their keys, their passwords to services, and the AI agent will go across and use them. And we'll look into that more in a second. But this is what the MCP is. It's a new standard for connecting AI assistants to the systems where data lives. And it provides a universal open standard for connecting AI systems with data sources, replacing fragmented integrations with a single protocol. And instead of maintaining separate connectors for each data source, developers can now build against a standard protocol. So let's look at that with a simple diagram. So here on the left, you can see Ivy. Now she works at Edera, and she is using the AI agent, which we can see here as a robot in the middle. Now that robot is connected onto the Edera database because Ivy's provided database information to be able to access it. Now the problem that we have here is that the AI agent might think that when Ivy asks for us to clean up the information, that means by dropping the database. And we've seen that recently where an AI agent dropped a production database. So where an MCP can help here is that we can put this in between the AI agent and our data source. So the AI agent connects to the MCP, and the MCP acts as an interface to, say, a data source or a service or whatever that may be within an enterprise estate or somewhere where you're holding private information. We can code onto the MCP to say exactly what can and can't be done by the AI agent. This might be providing information, this might be running tasks. It allows us to build up this interface. Now, you might be aware of something called an API, and an API was generated years ago for us to be able to access databases not via, say, a website. MCPs are very similar to that, but focus more towards AI agents. So much so that an MCP can have authentication in place. We can use OAuth to identify ourselves, so Ivy could identify themselves with the MCP to allow the agent to perform tasks on their behalf. So we're going to have a demo, and all this code is available, and there'll be links available to wherever you're seeing this recording to the demo code. So for this demo code, we've got Ivy, and they are going to use an agent, and the agent is going to connect to MCP Weather. So MCP Weather provides access to an application, and this application connects to a third-party service to be able to provide information about weather in a location. To be able to do that, the app requires a secret. Now, this secret is a token to access that third-party service. It's important that we have secrets, well, they remain secret, because if someone were to get access to this token, then they could pretend to be ourselves and have access to this third-party service. And yes, in this instance, this is about weather, but this could be for your database. This could be for another external third-party source that you're utilizing. So that's why we need to keep a secret. Secondly, we have bespoke code in here as well. Within our app, we've written an integration layer that connects to that third-party service and returns it back to the MCP. So we're going to use Claude to begin with here. And so I'm going to ask Claude, what is the weather like in Cardiff today? Cardiff, incidentally, is the city where I'm based in the United Kingdom, and surprisingly as well, it's sunny today. So Claude Desktop is using get forecast. Now we can see get forecast, and this is our MCP weather. Now, clicking on this, it shows me what it's passing. So I requested the current weather for Cardiff. Now, Claude Desktop has gone to get the latitude and longitude for Cardiff. Now, that's because the get forecast method requests it via latitude and longitude. So Claude's figured that part out. And then Claude has, if we go up here, we can see that Claude has returned the data. The MCP weather has returned the data to Claude, and Claude's reviewed this, and Claude has responded with more of an English response, more of a, dare I say, human response in a conversational way to see what the weather's like today. Now, there isn't just MCP weather running on my machine at the moment. I've also got MCP radar, and I've set that up with maybe some debugging intent, maybe some malicious intent. So let's have a look. Can you tell me the process IDs of any applications running index.js? So the Claude agent is now connecting to another MCP, and this one's got R on it for radar. Now, radar was able to go and have a look and find this information. We'll look more into how radar is achieving this in a moment, but we can see that there's a process of 73940, and that looks like this is the one that we want. It's running MCP weather. Okay, so let's see what else we could do. Well, now that we've got the process ID, so if I copy that, let's add into Claude. Can you provide me the environment variable for process? So I'm now asking Claude Desktop to get me the environment variables for this. Now we can see that there is something on radar called get environment variables. And this is returning the data that's being provided by the MCP, which includes the OpenWeather API key. Now remember what I said about secrets earlier on? Secrets are important to us. That is something that I don't want to be sharing with anyone, because now that you've seen that, I'm going to have to rotate that, because you could use that to be able to use the OpenWeather API yourself. And secrets are secret until we run them, and then they are run in memory. So this part of the attack is showing how we can leak the information, hence MCP. But there's something a bit more devious that we could be doing with this. So because we know the process ID, and we've found out where the application was running, and also this is an open source project, and this is part of the storytelling, but we can also say, can you show me the output variables for, now it's not index.js because we've got a weather util file. Now that weather utils file is what's connecting to that third-party service to be able to find out the information of the weather in the area. So this time, we're using lookabout and find out to look for these output variables. And we can see here that it's read the file and it's determined that there's an output variable called wind speed. So let's copy that and let's ask Claude, can you change the wind speed, the output variable, wind speed, to 133 miles per hour. So Claude has remembered in this conversation, it remembers where this file is that we've requested, and now it's asking for permission. To date, with everything that's happened, I've clicked always allow because YOLO. But I wanted to show here that we can also, when we're using desktop, we can allow permissions. Now, something interesting has happened, but let's see what happens with Claude Desktop. It says it successfully updated the output variable from wind speed to 133 miles an hour. But we saw that the wind speed, that there's a connection to MCP weather has been disconnected. And that's okay because we're used to restarting computers and applications. Now we can continue with this chat, but I'm going to ask Sonia and say, could you check the weather for today? I've just opened the door and I could see a cow flying past as it looks to be a bit windy. That sounds fairly British. Looks to be a bit windy. So what's happening now? So Claude is going to check the weather. It's going to get forecast. Now, we've used an MCP to change it so that instead of whatever was returned from the API, we've changed it to 153 miles per hour. Now, I don't think there's ever been 133 mile per hour winds in Cardiff. And we can see that Claude is now getting a bit confused, because if we have a look here in the get forecast, we can see that the wind is 133 miles per hour. So, well, no wonder that cow was airborne. No cow has been airborne within this demo. But what we're showing here is not only have we been able to get information via another MCP from another application, in that being able to access the API secret, we've also been able to edit the code base within an MCP, and now we're able to get false information that the AI agent is now using and returning back to the user, which could be more harmful, arguably. So let's go back to our slide deck and let's just review what just happened. So we had Ivy, and they were working with Claude. We'll call the robot Claude from now on. Claude Desktop, and Ivy asked what the weather was like in Cardiff, went to MCP weather, which went to the app using the secret, and the code was able to get the weather from the third-party data source, and that was returned to the app, which returned it to MCP weather, which returned it to Claude Desktop, reviewed it, and decided to give that feedback back to Ivy. Now, what I didn't share with you when we started was that there's another MCP called Edera. And this is on my machine at this moment in time. So Claude asked Edera to find a secret, and we did that by finding a process ID that got the environment variable, and we returned it back that way. And also we asked it to edit the code, and so we can see there's a malicious IV now in the code base, which is saying that the wind speed is 133 miles per hour. So whilst all that happened, the Claude was going back to MCP weather to find out what was happening with the weather and being told misinformation of being 133 miles per hour. So that is the attack that we just saw. Now, there's a problem here, and it's about isolation. It's a case of when we're running these applications, whether they be locally on your machine or whether they be up in the cloud or in your data centers, if we've got MCPs running next to each other, can they do the similar attack? Are they able to gain access to data from another MCP or other aspects on the machine, other processes running on that machine? And equally, are they able to read, write, and change our code base or other files on the machine? So we're going to have a look at a demonstration of the same attack, and we're going to use Kubernetes for it. Now, I'm just showing this diagram because this is, when we're using Kubernetes, we're using containers. So our MCPs are going to be in two separate containers, in two separate pods. Usually when you see this diagram, you'd expect to see solid lines around them. And I start to get concerned about this because when I see a solid line, I think of that as a security boundary. And so I can see solid lines around here, which act as a security boundary in those areas. By these dashed lines, I can see that there's dashes between from the process, there's a dash line in the container, the guest OS, the host OS kernel, and the hardware. Now, arguably, we do need to have dashes because if we weren't able to get information from the process out via the container to the guest OS, to the host OS kernel, to the hardware, we wouldn't be able to write to disk, we wouldn't be able to connect to a network card and be able to send information around. It's not going to be a good time. Our problem is, when it's as porous as it is, and we have this issue of potentially a leaky vessel, where processes are able to escape, and whether that being going from one container to another when we're not expecting to, or whether it's connecting to the hardware when we're not expecting to, or even worse, going out to the internet, and equally the internet coming back into these processes, this is what can cause concerns for security. So we're going to have a look at this now. Incidentally, this is the Claude config that I had set up for my Claude desktop. But going forward, I'm going to show you a tool called Inspector, which allows us as developers to debug MCPs. So the code base for both MCP Weather and MCP Radar are available on GitHub, and links will be available at the end of this, as well as wherever you're seeing this video, hopefully. So within this code base, I've got a couple of files. I'm connected to an EKS cluster at this moment in time. I was connected to it. One moment, please. Okay, I'm now connected to a Kubernetes cluster, and I'm going to run task Kubernetes apply. So this is going to apply the Kubernetes configuration to run a pod and a service, and we've also got a task here to do a port forwarding. Again, this is a concept for a simple demo just to show some considerations that you should have when you're running an MCP. So here I'm in Radar, so I'm going to run task Kubernetes apply. So again, this is going to apply the YAML for a pod and a service for Radar, and then I'm going to run task Kubernetes port forward. Port forwarding means that I can access this pod on localhost 3000 for MCP Weather and localhost 3001 for Radar. Now, I'm going to run Inspector. So before I do that, what is Inspector? Well, I'm running npx at model context protocol Inspector. It's just an alias, but this will run Inspector locally. And it will open up a screen. And this is what Inspector looks like. So we're going to just see if we can, I'll refresh the screen. There we go, connect. I don't think I can set up port forwarding. So let's go back to this task. Let's have a look. No, I did. I did. So let's just restart Inspector again. There we go. So there's our Inspector. So now we're going to use Inspector. Which is npx at model context protocol inspector, to be able to test out these MCPs. So if I run Inspector, this will open up a browser for me. And if I click connect, we can see that that's connected. Now let's take this to a bigger screen. And we also want to be able to connect onto MCP Weather, which is on localhost 3000. There we go. So this is a debugging tool to be able to inspect the MCPs. Sorry. So if I click List Tools, these are the tools that are made available to the AI agent. So we can get the forecast. Now, remember we saw latitude and longitude. That's because within this interface, it requires latitude and longitude. Now, even though I've done this demo several times, today alone, I can't remember the latitude and longitude for Cardiff. But there we go. So if I run this tool now, we can see this. So this is now using Kubernetes going across, and it is utilizing the API to get this information. The reason why you might want to run it on Kubernetes or just another computer somewhere in the cloud or a data center is because then you could just manage a single MCP and give this out to people who work within the same company as you, or offer this service to your customers to be able to access the data that we were looking at as we saw at the start in the starting slide deck. So as well as having MCP Weather, we also had MCP Radar. So I've got a get Radar status, and we can see that Radar is just hacking away. So we can get a process ID. So for this, I can pass a set of strings to search for. So in this instance, we're going to search for HTTP.js, because this time we're using a streamable HTTP to connect to the MCP. We can see a couple of process IDs here, but this is the one that's interesting to me, 22510. So I'm going to make a note of that here, 22510. So we're going back to inspector, and now we're going to get the environment variables, and this requests a process ID. So running that, I can see that I've got the environment variables back from the app via the MCP, and I can see that I've got the Open Weather API key. So that's how Claude Desktop got that information previously. Let's see if we can go a little bit further. So we could look to get the output variables, as we did previously in the Claude Desktop demo. So if I run this, run the tool. Now the MCP Radar has been set up so it's got access to the processes running on the machine, and you'll be able to see the configuration that we have within the YAML, within a GitHub repo. But this simply searches for output variables, and then that's what returned them previously. So our final part of the attack was to modify the string. So that was wind speed, and then that was to replace it with 133 miles per hour. So if I run this tool, we can see a success, modified one instance. So if we go back to our inspector for our weather, we can see that the wind was previously 7.82 meters per second. If I run this tool again with the same details, it's now wind speed is 153 miles per hour. So I've shown there that the attack that we did on Claude Desktop when it was local to my machine on my Mac, we did that attack without using containers. We've put the application into containers, and then we've taken it up to the cloud. And we've shown the attack path again, but this time using an inspector to get a better understanding as to how MCPs work and how you can test this out for yourself. So if we go back to the slide deck for a moment, this is a problem that we've just had. So this is back to the diagram that we showed when we were doing this locally. We've put the AI agent and we've connected it up into the cloud. So this line is representing going off in the internet into another machine. Now, like I said earlier on, we do need to have ways that we can connect onto things remotely. We need to use the network, we need to use disk, otherwise there's pretty much no point in compute. The concern that we have here is this dashed line here. Behind the scenes, MCP Radar was able to access the secret of MCP Weather and also write the code of the application. When I deploy an MCP, I would want that to be isolated. I would want to know that only things that I allow have access to this information. Equally, I want to be able to trust that the environment cannot be manipulated. So this is the Edera Protect solution. So with Edera Protect, we are a type 1 hypervisor, and so we're based above the hardware. Then what we do is that we create Edera Protect zones. Now these zones have the same containers with the same processes that you saw before. The difference here is that we're managing the guest kernel, and we are providing absolute isolation to each of those Edera Protect zones. The Edera Protect zone and the security boundary here is the Edera Protect zone. You get to decide what goes inside that zone. You get to decide what can see each other, and if it were to break out of it, these two containers could see each other, but they would not be able to see these containers over here. So if we zoom in a bit in the zone, we can see that the container is still the same. It's still got the guest OS. The container itself still has the same processes. It still has the same dashed lines. If there was a malicious intent within this process, it could still access this process here. The difference is that we don't have a dashed line all around this area, because the Edera Protect zone, we gatekeep where the I/O happens. So here we can see that we have a barrier to barrier to entry on the guest kernel, and equally that guest kernel has a smaller barrier to entry to get outside that guest kernel to the hardware. This is what allows us to have the isolation. So if we go back to our demo, so we're just going to clean this up. Task Kubernetes delete. So that one is for Radar. Okay, and then we're going to task Kubernetes delete. So first of all, we're going to defend our MCP Weather. by using Edera Protect. So Kubernetes, apply Edera. And then task Kubernetes port forward. Radar, we're going to keep exactly the same as it was. So that was tasks Kubernetes apply and task Kubernetes port forward. So again, we're setting it up as we did in the previous demo. The difference here is that we've applied this with Edera. Now, Edera is a container runtime. So the only change that we have, and again, you can see this in the code base, is that we've set the runtime of the MCP weather pod to be Edera, which essentially runs that pod within its own Edera Protect zone. So if we spin up inspector again, so we can see that we have access to the MCP. So let's just close these ones, open up and we'll open up another inspector and connect this one to Radar. So whilst we're getting this part ready, let's copy pasta this. So first of all, it's important to test that MCP weather is still working. There'd be no point in isolating it if it did not work. So we run the tool and it doesn't work. That's because I can't copy pasta. So if I run this now, it is working because I'm passing through the correct longitude. After this demo, I never want to do latitude and longitude until I go on holiday somewhere nice. So you can see that it's working, and this is running within Edera Protect. So let's go across and let's check out MCP Radar. Let's get our guest processes, add item. We're looking for http.js. Run the tool, and there's only 3 matches found. And we can check these 23165. So there we go, 23165. So this can see itself, and the only problem with inspector is it doesn't remember its state. So there we go. So we've got 23165, 23295, and 23297. 295. So we can see this. Well, that's the grep itself that we have running because that has now gone. So we've prevented the attack straight away by putting MCP weather into Edera Protect. MCP Radar is no longer able to see that information. So let's disconnect this again, and then we'll just swap it over. So task Kubernetes delete. Okay, so this time we'll revert MCP weather to being without Edera Protect. Task kubectl port forward. So we have that set up, but this time we're going to put Radar inside inside an Edera Protect zone. So again, this time we've just appended the pod YAML just to have runtime class Edera. So if I do cast task Kubernetes port forward, we set up our attack. Let's set up inspector. Okay, so now if we connect, so we can see that we've connected onto the MCP server, list of tools, process IDs, add item, http.js, run the tool. We see 3 again. We can't see the 4th one being MCP weather because we're running this within its own zone. So in the first demo with Edera Protect, we put MCP weather into its own zone, which meant that anything outside of that zone couldn't look in. This time, we've put MCP radar into its own Edera Protect zone, and that's able to see outside of that zone. So we've shown here how we can both defend a workload like MCP weather, and we can also defend an untrusted workload like MCP radar. So let's finish off with the slides. So our solution, the AI agent, is connecting onto MCP radar, but we see that MCP radar is unable to get the secret or the code of MCP weather because we've got the hardened boundary thanks to the Edera Protect zone. That's what's providing isolation, but we're still able to connect onto it via the AI agent. Well, that's it. That's my demo. Thank you ever so much for your time. That's the links to the code base for MCP weather, where you'll be able to find all the information that you have available. You'll be able to run this attack yourselves on your own laptop. Please feel free to reach out with any information that you might have. Thank you.